Next up, we have a presentation from Ofir, from Cadence. Ofir Michaeli is he's a verification engineer, manager, my apologies, leading MIPI and Unipol verification IP and JEDEC UFS memory model development at Cadence. Vice chair of the MIPI Unipol working group, Ofir holds a Bachelor of Science in Computer Science and Mathematics and is an MBA candidate at the Hebrew University of Jerusalem. So with pleasure, I bring up Ofir. We'll get his presentation set up here.
So I'm really glad to be here, and I really appreciate it that you all stayed until now to hear my presentation. So Ross talked a bit about CTS, which is provided by MIPI, Conformance Test Suite. And I'm going to talk a little bit more about those CTSs that are provided by the different working groups. And they are mainly provided for post-silicon testing, and I'm going to talk about how we can utilize them and use them in pre-silicon verification. Okay, so I will start with discussing a bit about the CTS, explaining what it is and how it looks like. I will talk about pre-silicon verification principles, the main steps to do basically pre-silicon verification, and then I will show you how you can use the MIPI CTS to do pre-silicon verification. So the main concerns that we have while going to do pre-silicon verification is basically deciding which part of the specs we want to check, which scenarios we want to cover, how do we want to cover them. We want to make sure that we are not overdoing that, we are not doing too many tests, and that we are not doing any redundant tests for features which we don't even going to use. Another concern is how do we create all those scenarios to make sure that we have 100% coverage of the specification. And after running all the tests that we already created, we want to make sure that we covered everything, and if something is missing, going back, recreating more tests and filling 100% coverage. And I think that the main concern is what do we do now when the spec change? How do we go back, review our verification plan, test plan, and make sure that nothing is missing, nothing is broken when we go and verify our new design. So the MIPI CTS, what is it? So the conformance test list is basically a list of tests that check the a device complies with a certain specification, and it enables some measurement of conformance for that device. It's used mainly, as I said, for post-silicon verification in labs. And when we go and write a CTS, we are trying to cover the main features of the specification. We don't always create tests for all the functionalities, but we are trying to cover the main functionalities. A product must pass all the conformance testing to be listed in the product registry. As was said, each CTS has a list at the end stating which tests are must, and only a device that passes all those tests can be listed in the registry program. But this CTS is not comprehensive enough to be used as a verification plan. When you go to do pre-silicon verification, you want to check all the features, all the scenarios with all the different settings, all the different capabilities of the protocol, and that's not necessarily defined in the CTS. So let's have a look at one CTS test. This one is taken from Unipol, for example. I will talk mostly about Unipol because I wrote a major part of the Unipol CTS, but I have a few examples from other CTS, like from CSI. So how does a test in the CTS look like? Each test has a purpose. It's usually 1 or 2 sentences describing what is the purpose of this test. What are we going to test? And briefly, how do we want the test to look like? We have a reference to the spec. We have a list of resources required if a certain test device is required or certain equipment is required, it will be described here. Usually we have a list of requirements in some annex. Last time this test was modified, a discussion. Usually it contains few paragraphs from the spec itself describing the functionality, how the certain feature that we want to test works, and some free text describing what are we going to do in the test scenario. A test setup, how do we want to connect the test device, which cables are used, SMA or any other like was discussed before, how the test bench should be constructed, and then the test procedure. I took a very short test, so it will fit the slide, but usually each test has around 10 different steps. There are tests which have more than 50 steps. And then the observable results. What do we expect to see from the device under test? Usually it's information which is observable on the physical link, but sometimes there are things which are internal in the DUT. So we describe the observable results here, but the tester should go and look inside his DUT to make sure that he did pass the test. And possible problems, for example, if we are testing a feature which is defined only in a newer spec and the device under test is an older device, or it supports only partial of the capabilities, then it will be mentioned here, and then engineers need to go and see whether this test is even relevant for their device. Okay, so what is pre-silicon verification? And basically, what are we doing? So pre-silicon verification is a software model-based program, in this case, that is based on a MIPI specification, and it's connected to the device under test. It's designed to run against any RTL on a cycle accurate level, and basically, and basically the verification engineer connects with a simulator to the device under test, runs a certain test and with the simulator, and then we can debug the results. And the 4 main steps of pre-silicon verification are defining the verification plan. I will go into more details in a second, but defining the verification plan, creating the test plan, creating the stimuli and running the tests, and then assessing whether the test passed or not. Let's start with the first step. In the first step, we are basically, we want to define the verification plan. And as I said, the CTS doesn't necessarily cover everything, so we need to create other verification plan items. But in that case, we are going to try and take a certain test from the CTS and see what can we do with that. So in this example, we are taking a DeFi test, and this test wants to verify that the DUT data lane LPRX properly aborts the escape mode entry process when a certain unexpected scenario happens. So we look at the purpose, and then we basically try to understand what does it take to verify that? What type of behavior we want to observe to know that this test passed or not. And then we add it to our verification plan and coverage model. And you can see here that we defined few scenarios which are linked to the same test case. For LP escape mode, you can see that there are a few types of errors that can be identified at different stages. And all the permutations of this error are required to ensure compliance in verification. So in the CTS, we usually define 1 or 2 scenarios, but for verification, we usually require that all scenarios will be tested. And then we grade them, we give them a score for each of the scenarios that happen, and we collect all the grades to know how much we covered already. Then we want to create some self-checking in our test bench to make sure that if such a scenario happens, we caught it and we gave some error message to the in our test bench to the device under test performing that scenario. Another example from Unipol, in that case, we want to verify that a NAC is being transmitted by the device under test when it receives a data or a control frame with a CRC error. And in the procedure here, you can see that we basically, first we finish the link startup, and then the tester is expected to send the data frame with bad CRC. And we expect, you can see that in the observable results, we expect the DUT to respond for that data with a NAC. And then we have a few more steps. We're sending also a control frame, an AFC frame, with CIRIC bit set and incorrect CRC. And we expect, again, for the DUT here to send a NAC for that as well. So in our verification environment, we are creating self-checking. So during a simulation, we expect that, if a NAC should be transmitted with an AREC bit and we didn't observe it, we will provide an error for the end user stating that no NAC with cleared AREC when expected. And then that check is also being collected and covered in the cover model and the verification plan. Okay, so the next step is basically creating some stimuli which is generated based on the scenario that we saw. So we define the test scenario with randomized constraints, and we configure the test setup to transmit some valid image or video sequence to the DUT for the DeFi example that we saw before. And then we modify the sequence to insert some invalid LP escape mode during the transmission. And then we repeat the previous step with different LP to make sure that we are covering all the different scenarios. And then the end user basically runs the test suite, and all those different scenarios are being randomized and tested, and we can achieve higher score for the coverage. Okay, and the last step is basically assessing and reporting the status of the completeness of the compliance. So basically, as I said, after we run all the randomized tests and which were created, we get a grade for each of the cover items in the cover model, which are also linked to the verification plan and the spec itself. And we get a grade for each of the scenarios. So we can see here that for the LP escape mode, we got 100%. But for other items, we still have some coverage holes. Here we got only 50%, and here even less. And we know that we need to go back. We need to refine our test suite. We need to add more tests, more randomization, and make sure that we are covering all the different permutations of the different error scenarios that might happen. And I think that the biggest question is, once you have reached 100% coverage, are you done? And then it's based on your coverage and verification plan. If it's based only on the CTS, then you probably should go back and invest more time in reading the spec and creating more coverage item because the current CTS is not designed for pre-silicon verification. And with that, I'm going to finish. So as I said, the CTS are aimed for post-silicon interoperability testing and not necessarily for verification. They are covering the main aspects of the spec, but not all. It can be leveraged for pre-silicon verification, but it's still not enough. You should still invest more in creating more complex scenarios, more error injections, more randomization, because not everything can be created in post-silicon, and it's easier in pre-silicon. And you should use each CTS scenario as a reference. You need to understand from this scenario what is relevant for pre-silicon and what is not. You need to adjust the test a bit to make sure that they are compliant by creating the completeness criteria. Is it even executable or measurable in pre-silicon verification? You need to understand how to create the self-checking logic based on the expected result in the CTS, which we saw before. You need to create some intelligence stimuli generator to create enhanced scenarios which are randomized and can be executed multiple times with different seeds to create different scenarios. And at the very end, get the report status of the completeness, see your coverage score, and if you still have coverage holes, go back, create more scenarios, more tests, and try to reach 100% coverage. That is all. Any questions?
Exactly. Maybe this question for the, just talk from Ross. Maybe you can answer it. He talked about those complete tests is available for the member. Can you tell a little bit, so like what including your test here for CTS? So what is available and in what form?
Are you talking about the registry program or only about the CTS?
Registered member for the MIPI. So, we're talking about some evaluation or the CTS test is available for the member, right? Mm-hmm. Do we have those list?
Sorry?
Available? Do we have those list?
The test list? They are provided for most of the protocols nowadays. Maybe Jim can provide more information from the test working group.
Yeah, the test working group does have the responsibility that has been delegated to them by the MIPI board to review conformance test suite documents, CTS documents, and those are provided to all the members when approved. So the documents originate in the technical working groups, not on the test group. This test group has an advisory function and review function. So there are CTS documents for battery, for camera, for display, for M5, for D5. I think the one for C5 does exist and is posted for C5, I think.
Yeah, I think.
And others are in progress as well. There is an older version for Slimbus that I feel is probably too incomplete to use. And each of the working groups has been told by the MIPI board to treat CTS development as equally important as spec development. In some cases, schedule pressure means that the spec arrives first and the CTS will arrive later. But CTS documents have become increasingly important for MIPI over the years. And we expect to see the pace accelerate to match specification development. If there's a particular technology, I might know whether the CTS is already available if you're interested in a particular one. For UFS, okay. That's a JEDEC specification, so we don't.
But the M5 and Unipol CTSs are widely used. Unipol has now CTS version 1.1 for Unipol 1.6 and 1.61, which are used by UFS. So basically, if you are going to test UFS, you need also to test M5 and Unipol. Mm-hmm. And they are widely used by all the manufacturers right now and also in our interoperability events. in Unipol we had 3 different interoperability events up until now. The last one was in Hsinchu City last year in October, and we have another IoT event next month, next to the face-to-face. So basically, all the manufacturers are coming to this interoperability event and connecting their devices and using this CTS to make sure that their devices are interoperable.
Mm-hmm. Good. Was that helpful? I hope so. Yeah, there is.
Yeah. The CTS is available in the MIPI website. All the CTS, the latest version, is available for MIPI members.
And older ones are in the archive also.
Yeah.
When you say the test, do you mean not the CTS document, some other document? Oh, as part of the registry program. Okay, yeah. For the registry program, a benefit of contributor membership in MIPI is that you can evaluate your own products and establish conformance and report that to MIPI. Adopter level members, the basic level of membership, will use a test house for that, and we're working with test houses to bring them into the program. So in each case where there is a MIPI CTS document, that is the basis for the conformance testing. For other products for which a MIPI CTS is not available, another test plan can be used if you provide the test plan to the program. Yeah.
They need to write them.
Yeah.
If they're defined in the CTS, they need to go and implement them.
Yeah.
They need to execute them, and then they can come back to MIPI and tell them, we passed those tests, and they get into the registry program.
Yeah, but in the case where there is a MIPI CTS document in place, that needs to be the reference.
Yeah.
So I hope that was helpful.
Yeah.
Good.
So I assume that the tests can test either like a DSI in or a DSI out. Is there any special testing that you recommend if you have something that looks like a bridge, where it's got an input followed by an output?
So in pre-silicon verification, it's quite easy. If your bridge is in RTL, you can just connect it to a VAP. I take it to my world. Let's say you have some bridge between Unipol and other protocols. So you can connect to your bridge from one side a Unipol VAP, and from the other side some application that you have, another VAP, and then you create your scenarios. You can basically stimulate those Unipol scenarios which are defined in the CTS through the Unipol VAP to your bridge and up to the application. So yes, it's doable.
That help? Anyone else? Well, I think that closes us out. Thank you, Ofir.
Thank you, everyone,
Much
for staying up
appreciated.
until such a late hour.